Well, good morning, everybody, and welcome to the first of today's webinars from Smart Vision Europe. We're looking at using SPSS in healthcare settings. If you haven't joined in these webinars before, just a few things you might want to bear in mind. The sessions are recorded, so you'll be able to listen to the recording afterwards. And there is some slideware here that I'm using. There's quite a lot of demonstration. I'm actually demonstrate different techniques within SPSS statistics, but there's a few slides that help explain and put a bit of context around the various procedures that we're running. So you'll get an email link that allow you to download a PDF of that after the session's ended. And if you think it's particularly useful for colleagues, we have done this before for people working in the NHS where we've rerun the session for a particular trust or something like that because they found it useful. You can do that. You can just send us an email and we'll see if we can find a mutually agreed time to rerun it. And with regard to asking questions, with all the lines are muted, so we ask you to use the chat panel, and I'll do my best to remember to look at that as we're going through the session and to try and leave enough time. But obviously, you can send questions afterwards, but just send us an email. And we are used to answering questions offline afterwards, those that we're not able to address properly within the session. Okay, if you don't know who Smart Vision Europe are, we are a technology company. We're accredited partner to IBM, as well as a company called Predictive Solutions and Data Robot, and we specialize in statistics, data science, machine learning, advanced analytics, all that type of stuff. Though we also work with open source technologies. We are providers of the SPSS product line. We're experts in SPSS and the various sister products associated with that. We're made up of a team that have about 15 to 30 years of experience working in the advanced predictive analytics industry. Pretty much all of us have worked for SPSS Incorporated at some point in time, and some of us for more than a decade doing that. I started in 1995 working as an instructor for SPSS and then became a consultant and a manager later on. And then ended up working for SAS Institute, if you know who they are, and IBM, before joining Smart Vision. So that means we basically got quite a lot of experience of stats and of data science, that sort of stuff, and applying them across lots of different sectors in the not-for-profit and the for-profit world. And certainly healthcare would be a key sector that we've got a lot of experience of working in. So our agenda today is to try and show a range of different procedures because doing analysis or applying SPSS in healthcare could mean anything. It could mean anything from experimental analysis, or it could be predictive modeling, or it could just be patient satisfaction analysis or something like that. There's a lot of different applications there, and as a result of that, we just try to take a tour through some of the more common, the most useful ones that people may or may not be aware of. So, for example, we've got a section on estimating odds ratios and relative risk scores. Odds ratios are used a lot within certainly healthcare analysis, and you'll see them mentioned a lot in reports and papers. And they're not always that straightforward for people to get their heads around. So we thought we would spend some time looking at that, as well as survival analysis, which is another standard approach to trying to work out the efficacy of different treatment plans and how these interventions affect survival time for different patients. So that's a classic technique. It's actually a family of techniques. We're going to be looking at that and helping you make sense of the output and the results of survival analysis. So let's start looking at patient satisfaction data. It's an easy way to start off. So we've got some classic satisfaction data that one might want to work with here in the form of a series of variables within SPSS statistics. These are just rating scales. So it's a classic sort of approach to analyzing any form of satisfaction. Rating scales are really commonly used. So we have a number of different factors here which are being measured, such as whether or not people are satisfied with their check-up appointment, the waiting time, admin procedures, hygiene and cleaning, that type of stuff, friendly healthcare workers, lab services. This is actually a data set which has been used to in on the internet. It's been made available on the internet to try and measure or try to test out different ways in which algorithms can predict an outcome. The outcome here being overall satisfaction. So if I just right click on that and show you what that looks like by going descriptive statistics here, you can see that 25% of people are actually very dissatisfied, 16% very satisfied. So it's a good mix from 452 cases, a good mix of different categories here and values. It's not like all the data squeezed in one category or the next. So it means that we can do some interesting analysis here. So one of the first things we might want to look at is does that satisfaction vary by the levels of another field in here? So we've got a field like age band. And if we want to analyze that, the classic way to do it, given that they're both category fields, is to go to descriptive statistics and call it crosstabs. And once you're in crosstabs, it doesn't really matter which procedure goes where, but I'm going to put age into the rows. And I'm going to put the variable overall satisfaction into the columns, and I'm going to go to sales and ask it for row percentages. So I'm looking at the percentage of each age group in terms of the satisfaction. If I click OK at that point, I just get a simple table coming out showing me the counts and many people who are 30 or younger and very dissatisfied, but also very importantly, the percentages here. And when we look at, say, very dissatisfied, the two extremes, and very satisfied, we can see that for younger people, the number of people who were very dissatisfied was 16.9%, 30 or younger, compared to 60 and over, where it's 35%, so more than twice as many. So looks like older people, as we move down through the age groups here, look like they're more likely to say very dissatisfied, and they're less likely to say they're very satisfied. So clearly there seems to be an interaction here between age and overall satisfaction. We might ask at this stage whether or not these differences that we're observing are in fact just random differences, or whether or not they are, they're being driven, or whether or not these differences exist in the wider population. In which case, we could rerun the procedure and we could ask for a statistical test. And the statistical test that we use here is the chi-square test. That's the most common one that's used. It's usually the first stats test that is taught to people. You can see also there's a risk. We'll be coming back to this procedure later on to get our relative risk ratios and our odds ratios, which we talked about mentioned earlier. It's one of our agenda items. So we can use the crosstabs procedure to generate those stats as well. In fact, as you can see, there's a lot of different tests here. Even if I click chi-square here, it actually gives me more than one test. But if I run it again and click OK, it just does the same thing again, except this time it's added a test box on the end here, a table, and the Pearson chi-square is showing what's called asymptotic significance, two-sided significance. That means it's two-sided, just means it doesn't have a direction. It doesn't mean that the older you are, the more dissatisfied you are, or the older you are, the more satisfied you are. It doesn't assume a direction, so it could go in either direction. And the fact is, it's giving us a value here of 0.041. Well, that value is a probability, and it's the probability of getting a result as extreme as the one that we have observed, assuming that age group and overall satisfaction had no relationship whatsoever, and that the two things were completely independent of one another. So if these two variables were completely independent of one another, it's possible that you could still get this result. I mean, it could just be a fluke, and that's really what it's showing us, is saying, well, it's possible that this is completely just the luck of the draw, that it seems that older people are more likely to be dissatisfied than younger people. But it wouldn't happen very often. In fact, you'd only see that result here it's indicating about 4% of the time, because it's got a probability of 0.04. And what we traditionally do in statistics, and it's kind of a rule of thumb more than anything else. It's not there isn't much science behind it, has to be said, but there is an arbitrary cutoff point, and that the most common cutoff point is 5%. So if it's less than 5%, we regard it as, to use the dreadful term, statistically significant. That means that the hypothesis, the null hypothesis that the two variables are completely independent of one another, i.e., that the age group and overall satisfaction are not related to each other in any way, that null hypothesis can't be supported, and we would therefore reject it. So we actually do a webinar just on interpreting significance tests here. We're brushing over it somewhat, but that's how you literally interpret that. And because it's less than 5%, the convention states that you would reject that null hypothesis. Now you can see here it's just less than 5%. It's actually unusual. You don't usually get something that's quite, 0.001 or it's 0.4 or something like that. You don't get something that's hovering just around about the threshold, but here it's just hovering around about the threshold of 5%. It's just below it. In fact, if you double click on these pieces of output and then say, what's this? It will tell you what it is. It says a significance level based on asymptotic distribution. Asymptotic just means estimated, basically. Estimated distribution of a test statistic. Typically, a value of less than 0.05 is considered significant. Okay. So here we're seeing a positive interaction or positive relationship here between, or a positive result, I guess, if you're saying we're rejecting the null hypothesis, we're seeing something that's statistically significant, and we're concluding that age and overall satisfaction are not completely independent of one another. We can reject that null hypothesis. And we could do the same thing. We could look at, we could say, okay, that's overall satisfaction. What about, let's see, exact diagnosis, satisfaction of exact diagnosis. Is there a relationship there? Well, as you can see here that people aged 30 or younger, 29% very dissatisfied, 60 and over 34.9% very dissatisfied. So it's kind of a 5%, 6% difference here. Turns out that that value is greater than 0.05. We would say there's not enough evidence here to reject the null hypothesis that age group and exact diagnosis and satisfaction of exact diagnosis are independent of one another. So that's one of the first things we're looking at here. What if we wanted to graph some of these relationships? This is kind of just a common thing that I do. I mean, sometimes showing cross tabulation tables can be tricky. So if I go to chart builder here and try to thinking of an audience which maybe isn't analytically sophisticated and doesn't really know how to interpret a crosstab, that still happens. We can ask for, say, I would use a stack bar chart commonly, and I would put the overall satisfaction variable commonly into this legend up here, which is the stack set collar. And I would put age group, let's say, along the bottom here. And when it does that, it's going to create a chart that looks like this. Okay, so that's a chart that looks like. Let's go back to it, call it up again, because it's still there. We can call it up again. We can make a few changes to it. For example, I can change the statistic from count to percentage. And I can say, okay, I want percent. This is saying percentage of what? And I'd say percentage of total for each x-axis. You can see now it's stacked to 100%. So you could actually, just so you're aware, you can actually do this after you produce the first chart. You could just click in here and say, click that button, and it would do the same thing, just changes it to 100%. So you can change it after you've created the chart. But let's go back to it again. Let's just say, look, these colors, they're a bit odd. We could change the colors here. I could say, okay, the first category is going to be red, and the second category is going to be like orange or something like that. Or I can go down to templates here, and I could choose a different. Template. So you can see there's different colors here we could play with. Or I could use my own settings. If I change it one time, I can create my own template. So I've got user specified here. We actually have our own chart templates that people can download from our website. So I've got one I use here for this one is called Lollipop. If I click on that, and you can see why, because it colors it. It's specifically for ordinal variables, for rating scale variables, where it's going from sort of hot to cool or from red to green to the traffic light. Clicked OK at that point. And here you can see that very dissatisfied is red and very satisfied is green. And we can see the relationship quite clearly here that as you get older, you get a larger proportion of dissatisfaction and a smaller proportion of satisfaction. Just so you're aware, if you want to put this into a report, you could copy it as an image. So I could go back here to my slideware and just say, okay, I'm going to put it into a report and do a blank here. Could copy it as an image. So here's me copying it as an image. So I paste it, it's just a raw image there. But another really good tip is if you right click on it and you're putting it into, Microsoft Office or something like that, you could copy it as Microsoft Office graphics object and then come back here, right click and just paste it. Hold on, I might have done that wrong. Let me just see, I noticed it was taking a while to react. Copy as Microsoft graphics object. Click back here, right click as, here we go, that's it. So you see it's copied it, not, it looks different now because it's being rendered as a bar chart within Microsoft Office. And I could go to chart design here and say, well, actually, I want that to be, change chart type. I want it to be stacked bar chart, stacked to 100%. I'll change the colors if I wanted to, or I can go to quick layout here. There's a lot of stuff I can do here. Change, apply a different template. What it's really doing is it's pasting the data that creates the chart in the background. So you could do that, you can play around with these and change the chart type if you copy it as a Microsoft graphics object, and assuming that you're copying a chart that Excel or PowerPoint or Word or any Microsoft graphics, any Microsoft Office application can make sense of. I mean, there are certain types of charts that are kind of specific to stats programs like SPSS, and they won't copy them across. But most of the basic stuff like pie charts and bar charts and scatter plots and histograms and stuff like that, you should be able to copy over them. So it's a useful thing to know about. Okay, this next thing we're going to come to is interpreting correlations. We're staying on the same data set here. So we've got interpreting correlations. Again, something that's very useful to know about when you've got rating scale, if you've got sort of satisfaction, whether it be staff satisfaction, patient satisfaction, that type of stuff, is that you can summarize the linear relationship between two variables using a single value. You can say how strongly related they are to each other. And that's because a correlation value produces a number that ranges from -1 to +1, or from +1 to -1. And the closer it is to 0, the more random the relationship is, i.e. indicating that there's no linear relationship. And the closer it is to either of these extremes, the stronger the relationship. So the charts I normally show these are from a data set called cars. Each one of these dots here is a vehicle, it's a car. And we have fields like vehicle weight and horsepower. Well, you could have exactly the same thing, like, between height and weight. These could be people. And here you can see it's giving me a correlation of 0.859. So if you look what that was, that's kind of round about here. It's not +1. It's not a perfect positive linear relationship, but it's kind of getting there, isn't it? It's starting to form a line, starting to line up, and it just indicates that as horsepower increases, vehicle weight increases, and as vehicle weight increases, horsepower increases. It does not mean that one is dependent on the other. It doesn't matter which way round the variables are. It's just saying, there's a correlation here of 0.859. Here's a weaker correlation. So this one's a bit weaker. This is 0.434. This is time to accelerate from 0 to 60 against miles per gallon. Saying that, yeah, if it takes you longer to accelerate from 0 to 60, it's probably a bit better on the MPG. And here we have a negative relationship, which is time to accelerate from 0 to 60 against horsepower. If it takes you longer to accelerate from 0 to 60, then you probably have less horsepower. So it could be like, alcohol, blood alcohol against reflex reaction time. You'd get a negative correlation there. It wouldn't mean that this is weaker than -0.7 is not weaker than 0.7. It's exactly the same strength. It's just that the direction is different. Okay, so that's how we can interpret correlation values. Let's look at how we can actually run them. If I go here to analyze and down to correlate and down to bivariate. Bivariate means pairs. I could pick up overall satisfaction, and I could look at some of these fields here that say checkup appointment. Let's pick a bunch of them here. Just look at them. Actually, let's throw them all in, actually. And if I do that, it's going to create a really confusing, very, very large table, because it's going to try and show me the correlation of every variable against every other variable. So I click that. Here it is, a massive table. The correlation is the first value that's shown here in each cell. So you see there's quite a strong correlation here, 0.5 between overall satisfaction and waiting time. The more happy they are of waiting time, the more happy they are of overall satisfaction. That's all that's indicating. Um, whereas age tends to be negative because it's saying the older they are, the less satisfied they are. It's not very strong. Correlations here aren't very strong. They're kind of quite small correlations, but they're there. How can I clean this up? Well, if I run it again, one of the tricks I can do is I can say, show only the lower triangle. What's that mean? Well, each correlation has repeated itself. So here we have overall satisfaction against overall satisfaction. I mean, that's a value of 1 because it's the same variable correlated against itself. That's useless. You can see the diagonal value is all equal to 1 because it's the same variable correlated against itself. And you can see checkup appointment against overall satisfaction here is shown at 0.487. And overall satisfaction against checkup appointment is shown at 0.487. So it's repeating itself. And we've got these diagonal values. We don't need either of these. We don't need it to repeat itself. So you can click back here and say, show only the lower triangle and don't show the diagonal. And immediately it gets a bit clearer. And the next thing you can do is you can actually double click on it and you can call it pivoting trays. These are throughout all SPSS output, table output. You have pivot controls, and it means if you've got a lot of information in here, you can take things like the statistics and put them into the layer box here. Now I can only see the checkup appointment. No, sorry, I can only see the correlations themselves, not the significance value, which isn't necessarily that interesting. We're really interested in the strength of the relationship. And you can do stuff at this point. You can start to play around with it and pivot it and change the table looks and things like that. Another thing you can do is before you even run the correlation, you can actually go to style here and ask it to highlight correlations above a certain point. So I'm going to say, show me correlations above 0.5. It's quite strongish correlations, 0.5. And I'll say, okay, look, I want them highlighted. That's a bit livid, that color there, so pale yellow. I could have it traffic light. I could add another layer here and say, between 0.3 and 0.5 or something like that, and just have them, I could play around with them if I wanted to. But I'm just going to add one here and hit continue. So just show me the strongest correlations. Click OK at that point. You see it's highlighting them. So I could double click on this and then put the statistics into the pivot box here, and we'd see where the strongest correlations are each time. So that's kind of useful. You should bear in mind, however, with rating scales, when you're working with rating scales, it's more appropriate to use these other forms of correlation here. This is called Pearson's. This is really for number fields. This is like, like the car data we saw earlier on. Doesn't make a big difference, but normally one would use Spearman's. Kendall's Tau B is slightly more accurate than Spearman's, but it's very resource intensive. So you can run that on a large data set and you just end up staring at the screen for a long time as it calculates the results. So Spearman's kind of quick. If you run that again, you get pretty much the same correlations. They tend to be a little bit weaker, but that's more appropriate. Spearman's rank correlation. Again, we have a webinar and a recording of that devoted entirely to correlations. Okay, that's correlations, and you can see how that would be useful when you're working with rating scale data and patient satisfaction data. What about working with decision trees? So decision trees can be used to do things like build profiles of staff, patients, research subjects, or to find key segments in data, or to generate predictive models. It does all of these things. And they're very popular because they're very visual representations of predictive models and of profiles, and they're relatively easy to understand. So what you're going to get is something like a family tree, or an inverted dendrogram, an inverted tree shape, where it starts with a key field. The key field would be something like, did the person relapse on a treatment, or were they readmitted to hospital, or what was the level of satisfaction with treatment, or what was the category of length of stay, some key outcome which could be affected by many other fields. And what a decision tree does is it picks that key, you choose that key outcome, you identify all your independent fields which could affect that, and it starts to build a tree to try to separate one group from the next. So for example here, we have a tree that just shows survival on the Titanic, where 67% of people did not survive, nearly 68% of people did not survive, 32% that survive. And the decision tree identifies, using a chi-square test that we saw earlier on, what is the key factor which dictated survival or not survival? What was the biggest discriminator between it? It turns out, of course, it's the sex of the passenger. 78% of 79% of men did not survive. 26% of women survived. You can see you start off with 2,201 people, and 1,731 were actually males. Only 470 were females. It starts to split them. And eventually it splits it out into a tree. So you can see here that survival on the Titanic, we can see that the men that survived, it splits it by age after that point. So it says that look, 20% of adult males survived, 40% of child males survived. So it's using the variable age here. And then it says, okay, I'm going to split it by class at this point. Why doesn't it put class under the child group here? Well, because either the group size is too small or it can't find another statistically significant variable to insert at that point. And if we look down through it, we can see the people with the lowest level of survival were actually males in second class. Only 8% survived, whereas males in third class, 16% survived. Males in first class, 32% survived. And crew, 22% survived. Over here in the female branch, we only have 470 records. It does not split it by age because age is not a significant predictor of survival among the female passengers. It just wasn't used. So it's really good at finding exceptions to the rule. And it actually finds groups that are not statistically different from one another, because here in the female group, unlike in the male group, it's actually grouped together second class and crew, because their survival chances were kind of too similar to one another. 87.6% of women in second class or crew members survived, 97% of first class survived, and 45% of third class females traveling in third class survived. So it's really good at that because it's very visual. It's finding the key segments. It's finding the sections to the rule. It's building a profile of people in terms of category outcome here being survival. And it's also a predictive model at the same time, because you could apply this to new data and it would pick what we call the terminal nodes, these boxes here, and it would show you the percentage chance of surviving. You can use it to model satisfaction. So for example, here we have when will employee leave, and we've got, attitude of senior staff is the key factor which dictates whether or not they remain at least 5 years or leave in 2 years, that type of stuff. So you can use it for lots of different applications. Let's have a look here. So if I wanted to run it here, I could go down to classify and down to tree. And I'm assuming overall satisfaction is kind of the logical thing to work with here. Actually, I'll show you something. If I just run this quickly, I'm just going to run it quickly. This can't, something to bear in mind is that one of the issues here is that we've actually got 5 groups in the overall satisfaction group. So it's really hard. You see it highlights the modal group, the group with the category with the most cases in it. So each time, so it helps a little bit with interpreting it, but it's actually quite difficult to interpret here because we've got 5 groups. So what I'm going to do is just collapse together the dissatisfieds and the satisfieds and neutral. So we get it down to 3 groups. And I do that just by running a recode procedure. The recode procedure is standard procedure within SPSS. It helps you move categories around. We have a video online that shows you how to do that. So here's recode in the 3 group satisfaction. If I just run that as a piece of code here, it creates a new field for me called overall satisfaction 3 group. And I'll just run it again. We'll swap these around. And I'm just going to give it a little wiggle room. I'm going to say, okay, I'm going to let you go down to quite small group sizes of, say, 20 and 10 or something like that. Or actually, maybe 40 and 20 would probably be more sensible. It's using the chi-square algorithm at this point. So it's an algorithm called shade. There's more than one type of decision tree one could run. Click OK at that point. Double click on it and look inside. Let's have a look. Did I do this properly? Oh no, I must have done it incorrectly. Hold on. Yeah, I didn't swap it across. There you go. Let's do it again. There we go. Okay. So it's built it really quickly. As you can see, it's run all these tests. And if I just zoom in, I can see that You got dissatisfied, neutral, and satisfied, 452 cases. What's the single biggest factor which drives, people's level of satisfaction? It's actually the level of satisfaction of exact diagnosis. If I show ranges as text here, you can see that people who are dissatisfied or less with their exact diagnosis, 81% of those people are in the dissatisfied group, as opposed to the baseline of 47%. Whereas, if they're higher than satisfied, very, very satisfied, in other words, very satisfied with their exact diagnosis, and 93% of them are in the satisfied group, overall. And if you're kind of looking for opportunities here, you can say, look, for example, 70% of the people here are who are better than neutral through to satisfied with their exact diagnosis. If you wanted to boost that number of their satisfaction level, you find that if they say friendly healthcare workers and better than neutral, just better than neutral, that goes to nearly 90%. So you can see here it's finding the for each branch where the next factor is, it splits that, and we can see a sort of hierarchy of factors here. In a similar sense, if I just jump to another data set, I'm going to open up another data set now, and I'm going to open up a data set called let's see, surgical treatment. I think it's called the patient length of stay. Sorry, let's see. I just need to find out one patient length of stay decision tree. There you go. So this is a LOS length of stay decision tree. I think I've got yes, I've got this is called a variable set. You can define a variable set, which is a subset of variables. You can do it here by clicking define variable sets. It just makes it easier when you're working with a lot of different variables here. If you only want a subset of them. So I've got a little variable set called decision tree here, which I'm going to switch on and just say, show me new variables and show me the decision tree. And it just masks out lots of the fields here. So I've got a key variable here. I'm going to call up decision tree again. I've got a key variable here called surgery result. And we can see that it's well or other, where, there was actually a lot of different outcomes here, but some other could include things like death or relapse, something like that. And I can pick up all these fields. So I've got these fields, including surgery treatment, and say, what really governs the surgery result. I'm going to make that 20 and 10 in terms of my smallest group sizes. Click OK at that point. Get to run that. It's taking a bit longer to run it. And let's say if I double click on it and zoom in, I'm going to add some bar charts here just to make it a bit clearer and zoom in. You can see the single biggest factor is the type of treatment that they had, whether it was a PTCA or a CABG. And if it was a CABG treatment, then the type of drug that they were using, whether it was a clot-dissolving drug. If there was no drug, as a suboptimal results, 59% was something other than well. So, whereas if they use Retaplays or Alteplays, it's actually 77% of well, or streptokinase, it's 56% of well. And you can see then things about, their cholesterol level, whether it was normal or high, or a history of myocardial infarction. In fact, I could go back to this and say, look, let's ignore the surgical treatment. Let's take that out and say, ignoring the surgical treatment, what drives people's survival? Or sorry, people having a good surgical result. It doesn't always result in death, of course. And the next thing it picks is the type of clot-dissolving drug that they had. There are situations here where people saying, okay, they had no clot-dissolving drug, but they had no history of angina. So 85% of those people, don't need a clot-dissolving drug. They have a good outcome. If they did have a history of angina and they didn't have a clot-dissolving drug, then it's 68% or well. So it's just a lower value. Here it's saying, if they have one of these two clot-dissolving drugs and their cholesterol is high, then 85% are well. And history of angina, 83% are well. So you can start to see how the factors, whether or not they're physically active, how these factors interact with one another. That's why the CHADE algorithm, if you look at the kind of what it stands for, so that's for chi-square automatic interaction detector. This is really useful. We can also see the accuracy of the model. It's actually The accuracy here looks like it looks like it's completely inaccurate because it's not predicting anybody to be in the well group, but that's because sorry, in the other group. But that's pretty arbitrary. That's just basically saying, I'm trying to find people with a greater than 50% chance of being in the other group. And there aren't very many situations where people are more than 50% likely to have a suboptimal outcome, because more than 50% chance of that happening would be huge. But what you can find are situations where people have, a much higher than 18% chance, which is the baseline. So, if you're looking at groups here, like 29% chance of having a non-optimal outcome, or a 40% chance. So it's really good at finding these hot spots where we're kind of we're trying to find increased levels of a particular outcome, whether it be dissatisfaction or readmission to hospital, or in this case, recovery from surgery. So decision tree is really powerful way to model data, to look at the relationships between multiple factors at the same time, and to build a multivariate model, which is pretty visual in nature and not too complicated to get your head around. Okay. Having looked at that, what about the next section? Next section, we're looking at odds ratios and relative risk scores. So I wanted to spend some time. I put some videos together on this because I just know it's an area that people get very, very confused over, and understandably so. But they're used so often in measures of risk. They play a crucial role in healthcare, and they've been doing that for decades, and for several reasons. These little statistics, these little values are used for assessing treatment effects, measuring the impact of treatment, interpreting clinical studies, comparing treatment effects from one study to the next. Public health decision making, evaluating vaccination programs. That's one of the values which is used to try and figure out whether or not a vaccination program is working. And often when they're dealing with risk communication, they're trying to say, look, the effect of using this particular drug as opposed to that drug, or the effect of having this condition versus that condition, can be measured using an odds ratio or relative risk ratio. And also used in identifying high risk populations within a wider population. Now, there are two key measures of risk which are commonly used, and they're both present in SPSS, and you get them both when you ask for the risk measures in the statistics sub-dialog of the crosstabs procedure: odds ratio and relative risk ratio. So these are both what are called measures of association. That's just by the by. It doesn't really tell you much other than that. But rather than looking at whether a relationship is statistically significant here, we're not really trying to, well, it's not our key. It's not the key thing that we're focused on, whether or not we reject or accept a null hypothesis. What we're trying to do is measure in some way how strongly two factors are related. In healthcare applications, these values can indicate if exposure to a factor can increase the risk of an outcome, or conversely have a protective effect. And we can also use what are called confidence intervals to show if the effect is statistically significant. You don't have to just use a p-value. Confidence intervals can tell you if an effect is statistically significant, to use that term as well. One method, as you might guess, is based on odds, because it's odds ratios, but the other one's based on probabilities. That's the relative risk estimate. Okay, so before we get into that, we need to talk about odds versus probability, because these are often confused and they're slightly different, and the interpretation is slightly different. So if you roll a die and you're thinking, what's the probability of getting the 6? Well, it's 1/6. That's what that is. That's what the odds is, or 6-1 against if you're betting, putting a bet on it. So 1/6 works out as a probability, or as a percentage value of 16.7% of occasions. So it's saying of 16.7% occasions you will roll a 6. Okay. So that's the probability. That's the probability. So you get 1 out of 6. So 6 possible outcomes. So there's only 1 6. Okay. That's the probability. The odds are different. Odds are 1/5. So it's kind of 5-1 against this, what a bookie would place that. And the reason why this is kind of subtle, but it makes it important to understand, is that for every 6 rolls, 5 of them will be a number other than 6. So you might just think that that's, that sure, that's just a different way of expressing the same thing. You're saying, how many sixes do you get out of all possible outcomes versus, how many sixes do you get versus how many alternative outcomes can you get, which is what odds are. So odds are calculated differently from probability, but it turns out that odds are used a lot in statistics because they have certain mathematical properties, which is kind of too hard to go into at this stage, but there's certain mathematical properties associated with them, which statisticians tend to like a lot. And it just means that they're going to pop up a lot in publications. So if they are going to pop up in publications a lot and we need to make sense of them, then that's what we're going to do and address here. Okay, so an odds ratio is the ratio of odds, not the ratio of probabilities. It's the ratio of odds of A in the presence of B and the ratio of A in the absence of B. And because they're odds, they're generally regarded as a bit more difficult to interpret than the alternative approach, which is relative risk ratio, ratio of probabilities, i.e. the probability of an outcome in an exposed group to the probability of an outcome in an unexposed group. Okay, so that's what we might want to do. So in this example, we're going to look at the associated risk between smoking and angina. And here the risk factor, of course, if we think about it, is smoking, and angina is the outcome. And we can use the SPSS crosstabs procedure to compute both the relative risk factor and the odds ratio. So I'm just going to jump to the data set here to do that. Go to File, Open Data. And there we have odds ratio and relative risk. There's our two variables here. And just to keep us on the straight and narrow here, I've actually going to show you what the outcome looks like in the slides and kind of annotate everything as we're going through it to make it nice and clear. So I'm going to take the variable age, sorry, the variable smoker and the variable angina here and put them into a crosstab. So if I go to Analyze down to Descriptive Statistics and down to crosstabs, I'll put this variable here, smoker2, I'm putting that in the rows. And I've got this other variable here, angina2, which I'm putting into the columns. And you notice I've got two copies of these variables here. So angina 2, smoker, smoker2. It's because I've used recode to shift the categories around, and you'll see why I've done that in a moment. If I go here to sales, I can ask for row percentages. Click continue and OK. We're going to get an output that looks like this. Okay, so there we go. 68% of the how many people are 10,000 in this sample, quite a big sample. 68% of the smokers had a history of angina, and compared to 44% of the non-smokers, 31.8% of the smokers did not have a history of angina in this population, in this sample, and 55.6% of the smokers didn't. So that's kind of the relationship. It does look like smoking. Certainly, if we did a chi-square test here, it comes out statistically significant. Does increase the risk of having angina. So the key here is that the outcome has been put into the columns and the risk factors put into the rows. Now, normally in you're doing cross tabulation analysis, it makes no difference whatsoever which variable goes in which column. It makes no difference what the order of the yes and no group is. But it turns out when you ask for it to calculate risk, odds ratios and relative risk categories, which variable goes where is important, which is why I've gone to the trouble of marking it up here. And more importantly, I've made sure that the first value is the positive result. Yes, they have angina, and yes, they are a smoker, because it also uses these values here and it assumes that the positive value, so the outcome value, that they have the condition and they are exposed to they're exposed to the risk factor is indicated in the first value here. So I've run recode to make sure that they've got that the first value occurs in that, and you can see that when I go to crosstabs here and right click on these, you can see that yes is the first value that appears, and here yes is the first value that appears here as well, and no is the second value. If I go to statistics and ask for risk statistics, it kind of assumes that the condition is in the rows and that the outcome the risk factors in the rows and the outcomes in the columns, and it assumes that the thing that indicates they have the condition and the thing that indicates they have that outcome is the first category in each of these. If I click OK at that point, it'll run that procedure. And what we get is this risk estimate table that's been added at the end here. So let's have a look at that in a wee bit more detail. How's it working out these numbers in those risk estimate table? Well, first of all, for the odds ratio, which is the first thing we're looking at, it simply looks at the two counted values for the yes and no for those who are smokers, and it says, okay, if I look at them as a ratio of one to another, it comes out as 1552 divided by 723. That gives me a factor of 2.147. I just do the same for the no group. Just the two cells here and look at the ratio of those. That comes out as 0.797. And if I look at the ratio of these two ratios, which is the odds ratio, that gives me a value of 2.69. What does that mean? It means the odds of having angina are 2.6 times greater for smokers than for non-smokers. That's literally what it means. The odds of it. That's the key, is not the probability, the odds. This is a measure of association. It is not a causal statement. So if you ever have to interpret the odds for something like this, it usually means that the odds value is normally the risk of, you know, of having that condition and being exposed to that particular risk category. Okay. What about the relative risk ratio? Well, in this occasion, it's not looking at the yes and the no and looking at the ratio of those. It's actually looking at the yes compared to all cases. So how many yeses do you get as a proportion of the total? What's the proportion of that? Well, that's 68%. As you can see here, it's just 0.68. It's the same as that value. And the next value is the proportion, it was basically 44%, comes out as a ratio of 0.44. And then the ratio of one to the other is 1.59. And it's simply interpreted as the probability of having angina is 1.54 times greater for smokers than for non-smokers. Whatever that baseline probability is, think about it. I mean, you could have a condition here which is very rarely occurring. You know, it could only occur 1% of occasions. And, you know, you could have a risk ratio of 1.5, which would mean that, you know, it's if you have that condition, or if you expose that risk group, that the probability of having the outcome is 1.5%. And that's different from being, you know, if it was a 30% of the data had the outcome, had the condition, and you had a risk ratio of 1.5, that would mean that, you know, it jumps from 30% to 45%. So the baseline probability has to be taken into consideration. It could be something that's very rarely occurring. Now, you do get different numbers here for this table, obviously for the odds ratio and for the risk ratio. And here the values, as we see being shown here for the odds ratio and the risk ratio, exactly the same values that we have calculated. It says, although the odds ratio and risk ratio values are quite different here, generally speaking, these two numbers start to become much more similar to each other when the proportion of people with the condition occurs relatively rarely. Once it gets below 10%, they start to really converge and they're kind of very similar. What about these values here? Well, we don't have a statistical test, but these are confidence intervals. And they're simply showing here that the odds ratio could be as low as 2.4 or as high as 2.9. The point is that they're both numbers which are greater than 1. So it's an increased risk. And therefore, we would say that's statistically significant. If one was 2.4 and the other was, you know, if one was 0.5 and the other was 2.1, well, one's lower than one, so it's a lower risk, and one's a higher risk. So it would indicate it was non-significant. So, but if they're both above 1 or both below 1, it indicates that they're statistically significant. So for the odds ratio and relative risk ratio, both of the intervals are positive, so this, or higher than 1, so this indicates an increased risk of effects in the population. Okay, that just gives us enough time to look at survival analysis, which is the last thing we're going to look at here before we wrap up. Survival analysis refers to a family of statistical procedures where the outcome of interest is time until event occurs. It's commonly employed where researchers are interested in modeling the effects of different treatments or conditions upon patient survival time. And for this reason, survival analysis is a key technique used to analyze the efficacy of pharmaceuticals in studies of disease prognosis. So it's often referred to time to event analysis because it uses what's called TTE data, time to event data. And basically, that just means a data set that's composed of two key fields. One of the key fields is, has this event happened, yes or no? And of course, it's fair to say that the event is normally death, that, the person has died, but it could be something else. It could be, in this case, it's whether or not a drug has taken effect, or it could be whether or not they've relapsed, or whether or not they get readmitted to hospital. Survival analysis is actually used in insurance analysis, where they're trying to figure out whether or not a claim has been, what the probability of a claim being made. So that's one thing, the outcome. And the second thing is just how much time has elapsed before the event occurred. So how long, have they had this condition, or how long have been a policy holder, how long have they been in hospital or whatever. So those two factors allow us to do a survival analysis. One thing you do have to be aware of is something that's unavoidable with survival analysis is something that's called censored data. And that's a term that uses for unknown circumstances where we don't know how long the patient survived or how much time elapsed before the event occurred. So it's kind of like a missing value. It's an added complication of the analysis, but it's one that the analysis has to incorporate into the various calculations to estimate survival time. So different examples of censored data would be something like this. You're doing a study and you're looking at people who've had a condition from a certain point in time to the point at which an event occurred. And you know when it started and you know when the event occurred. So it might be when they, you've been monitoring for some time. So that means it's not censored. But it could be possible that they just drop out of the study. You just don't know what happened to them. You don't know if the event occurred or not. That's called right censored data, and it's shown here as a plus. So it's like a missing value. We know that they were still alive at this point. So it's still valuable data. We know that they still survived at this point, but we don't know, at what point they died, because everybody dies eventually. And that's, of course, what the third situation here says. Look, they survived all the way through the study. The event did happen, but it happened outside of the framework of the study because you got to stop at some point. You can't, it happens some point after you've done the analysis. Or you don't know when the event started. So you don't know when the condition started. If there's some sort of, medical condition, cancer or something like that, you don't know when they first had it or when they developed it. If they're doing something like annual checkups, something like that, you just know it happened at some point during that year or some point within the past 2 or 3 years. So you don't know when it actually started to happen. So there's different ways in which censored data can arrive. Okay, we're going to run a survival analysis, and the key here is that we're going to get 3 key bits of output. The first bit of output we get is what's called a cumulative survival table, which just tells us the proportion of people who are surviving, over time for the different treatment groups that we have. The second table is group comparison tables or tests. That tells us whether or not one treatment is statistically different from another treatment. And the third are graphical plots, and the survival plots, there's different types of survival plots, so we need to talk through them. So the type of survival analysis we're going to do here is a classic type called Kaplan-Meier survival analysis. And the sample data set contains 200 rows of data. Each row represents a patient receiving an anti-inflammatory medication for chronic arthritic pain. And the time to event variable is the time the medication takes to have an effect, if it has an effect at all. I actually don't know what that's measured in. I'm assuming it's minutes. I don't know. The event variable denotes whether or not, the effect occurred, whether or not their pain was reduced, or whether the data was censored. It could be censored because they said, no, look, I need a different treatment, or they were moved off the ward, or they said, I can't handle this. Can I have something for the pain? And therefore, they're effectively taken out of the study. A key additional variable measures whether the treatment was administered with a new drug or the standard medication. So we're comparing the new drug versus standard medication and seeing if that affects the survival time or the time at which the treatment kicks in. Sample file is called pain medication salve, and it's included in the samples folder where SPSS is installed. So this is what the Kaplan-Meier dialog box is going to look like. I'm just going to set that up very quickly here. Let's see, it's called pain medication. Where do I go to do that? I go to the analyze, down to survival. You can see there's a family of different survival procedures here. I'm choosing Kaplan-Meier. It's kind of the standard one. The time is time to effect variable here. The status variable is whether or not it had an effect. So we just need to check that and see what that is. That's censored or taken effect. So one or the other, you know. Either didn't take an effect and it's censored. We don't know what happened if it ever did take an effect or they taken out of the study, or it had an effect. And category 1 indicates it had an effect. And then I'm going to put in the treatment type. That's going to be what's called the factor variable. And that has the new drug or the existing drug. And then I'm going to ask it to do a couple of statistical tests for me. And I'm going to ask it to produce some plots for me. There we go. Click continue that point. So these are my settings that I'm creating here to rerun this. So if you've got a copy of SPSS, you can reproduce this output using the pain medication data set, which is in the samples folder. If I run that procedure, this is the output I get. First of all, I get a big survival table, and it's showing me, it's basically two tables, one on top of the other. It's got the new drug at the top, and then at the bottom, it's got the survival table welded onto the bottom of that for the existing drug, so the standard treatment. And then after that, we've got some means, some just averages. It's just showing us confidence intervals. Some percentile values, some statistical tests in overall comparison, and then a bunch of plots. So let's work our way through these. First thing we get is a survival table here. And basically, the survival table is simply telling us for the new drug here initially, the time to effect, so 0.6 minutes, two patients had an effect at the same point here. So that means the event occurred at that point. So, you know, or 0.6 hours, it could be 0.6 hours. That's the event occurred at that point. That means that two events have occurred. Taken effect is the status, just noting it's taken effect. Cumulative survival is the proportion of non-censored cases where the effect has not occurred. So at 0.7 minutes in here, with 97% of the cases, it still hasn't had an effect in. The standard error is an estimate of the variance or the cumulative survival. It's kind of an estimate of the measure of kind of reliability. That value will get larger as you start to run out of cases because you can be less, the statistics start to become less reliable. And the cumulative account is just simply counting up how many times the event has occurred thus far. When you get to 0.9 hours, we've got 99 remaining cases in that group where the event hasn't occurred. So the number of non-censored cases remaining where the effect has not yet occurred. Pretty straightforward to interpret. It's just showing you how many cases are still left. And it does that for both drugs. Then we get our means and median survival table. It's just showing us what the mean survival time is. The mean number of time for the new drug to take an effect was 4.87 hours. That's the average. And for the existing drug was 5.1 hours. So it's not a big difference. Some percentiles here is just the median value, what the effect is for the top 25%, for the bottom, but by the time you got to the 75th percentile, 75% or 75% of the data have had an effect about sorry, the bottom 20, the highest values had an effect at 1.9 hours and 2.4 hours. The median values here, 3.7 hours, 4.1 hours, are exactly the same as median values up here, 3.7 hours and 4.1 hours, with confidence intervals around it. And it gives us some statistical tests here. It's saying none of these differences that we're observing, it's just 3 different tests here of new drug to existing drug, are statistically significant. So there's 3 tests here, and they basically log ranks the most basic one that says all the time points are weighted equally in this test. Breslow, time points weighted by the number of cases at risk at each time point. Less power when the percentage of cases is large. Early events are weighted more heavily than later events. So it's an adjustment for the fact that when you have earlier in the data set, earlier events, you have more data. So you have a smaller standard error. So it's a bit more, it's paying attention to the fact that you've got a lot more data. Log rank doesn't pay any attention to that. And Tyrone Ware, time points are weighted by the square root of the number of cases. Basically, it's regarded as a compromise, these 2 ones. So Tyrone Ware is a good one to start with. The point is that they kind of give similar results. That none of the treatment outcomes are not statistically significantly different from one another. And when we look at the associated charts of that, the charts are simply charting what we saw in this table here. It's just basically taking these proportions here and charting them for us. So the survival table is saying, at 6 hours in, this is the proportion using the new drug where where the treatment effect hasn't occurred yet, whereas using the existing drug, it's a wee bit higher. So it does look, if you're looking at the chart here, it does look like the new drug has an effect slightly earlier than the existing drug, but it's not statistically significant. So this is a cumulative survival table. By the time we get down to 12 hours, there's about 10% of the data where it still hasn't had an effect for the existing drug for this. Yeah. 1- is just the same chart, but in the opposite direction. So it's just saying, what proportion is the effect, what proportion is affected by the drug at that point. So 80% have been affected by it. It's kicked in for 80% of the cases, maybe 85% of the cases, about 9 hours in. And then, so it says the cumulative function here denotes the probability the person will survive beyond a given time point based on the rate of occurrence. The hazard function denotes, however, the rate of failure of non-survival occurring at a given time point based on the fact that the subjects have made it this far without encountering the event of interest. And the reason I'm pointing that out is you will see things like cumulative hazard functions plotted. And the point here is that this is a rate. It is not a percentage. And a rate is different from a percentage because a rate is telling you how many times it happens in a time point. So if the periodicity was measured in years, for example, you could reach a time point where a given event like a stroke or something like that might be occurring on average 1.5 times a year, or a fall or something like that. If it's over 3 years, twice over 3 years. So so the cumulative hazard does look different from this 1- survival function because it's actually showing the rate at which it's occurring. By the time you kicked in at 8 hours, you'd be expecting it occurring 1.5 times per at that once you've reached that point. That's the rate of occurrence. So the rate of occurrence is increasing as the hazard increases. Okay, just a few things to bear in mind. We have some useful video resources here. When you get your PDF download your PDF of the slides, you can click on these values here, these URLs, and they'll take you to some videos that go into this in a bit more detail, a bit slower than what we've done here. So if you find it really useful, you can look that up. And we can help with transforming and analyzing your own data. We offer training courses, virtual training courses, in-person training courses, and consultancy and training where we do the initial work and then teach you how to replicate it. You can buy the software directly from us. We offer training and general advice and no strings attached support to people, whether they're customers of Smart Vision or not. If they just reach out to us, we will try and answer those questions as we're going along. And yeah, last of all, we just thank you for attending today. I hope that you found it useful. If there are any questions, we are out of time. If there are any questions, we'll follow up with you offline. Do feel free to reach out to us, and we'll do our best to answer any questions that you have. Thanks very much. And if you want to log into the next session, that's in a couple of hours' time, where we're looking at regression methods and how we apply them in healthcare settings. Thanks very much.